Now suppose that you have two populations that you would like to compare. Maybe you have two different machines and you want to see if the machines are still producing parts with characteristics at the same level. Another example might be that you have a new drug and you want to see if it does a better job treating an illness than the present treatment. There are many other situations where you may want to compare two populations. In this lecture, we will discuss how to do this. We will do this utilizing two-sample hypothesis testing. This can be done with pretty much any summary measure. We will focus on means and proportions. Let's start with means. Suppose that we have two independent populations and we would like to make a comparison based on the means. Now we take a sample from each population. Just as in when we wanted to make inference with one population, we will create a hypothesis test for this situation. In general, we would set up the null hypothesis as the difference between the two means is equal to some delta naught. In most cases, delta naught is equal to 0, so the null hypothesis will be that their two means are equal. If we assume that the populations are independent and that both variances are known, not necessarily equal, then based on the central limit theorem, we can use the test statistic given on the screen. Notice that this is a z-statistic, which means that we can utilize the standard normal distribution to calculate p-values. So how do we do this? The table on the slide tells you how to determine the p-value for the hypothesis test based on the alternative. You should be able to see that this is really no different than what we saw for the one-sample test. Notice the table also gives you the rules for using the rejection region method. So in this case, we know what the variances are. But what happens if the variances are unknown? If the variances are unknown, then we cannot use the test statistic on slide 3. There is something called large sample theory, where if the sample size is large, we can assume that the sample variance is very close to the population variance. I am not a fan of this. There are different trains of thoughts on what sample size is big enough. Some say 50, some say 100. To make your life easier, you should only use the z-test if you know the variances. So if the variances are unknown but the variables come from a normal distribution, then we will use the t-test. The test statistic for the t-test is given in the slide. Now let's talk about degrees of freedom. Recall that the degrees of freedom is just the amount of information available in the sample. When we were discussing the one-sample t-test, the degrees of freedom was calculated as n-1. It is much more complicated for the two-sample test. We calculate the degrees of freedom for the two-sample test based on the equation in the slide. Notice that based on this equation, you may get a degrees of freedom that is not an integer. Most computer packages will still be able to use this. If you are using a table, you should always round up. Here is the table with the alternatives and how to find the p-values. You should be able to see that this again is similar to what we saw in the one-sample case. Also, this includes the rejection region method. Let's do an example. In this example, we have two different hardening processes. The question is asking if you believe that the mean hardness level for the salt water is less than the mean hardness level for the oil. This is giving us what the alternative should be. It is the research question. So the alternative hypothesis will be the mean of salt water is less than the mean for oil. Notice that we have been given the information that the variables are normally distributed. And since we are only given the data, we can assume that the variances are unknown. Sample data is given on the next slide. Here is the data. We can see that the sample sizes are the same. Let's take a look at the solutions. Here are the solutions. Notice that the mean difference is based on salt versus oil, and the sign in the alternative is less than. Recall that we wanted to know if the mean for salt water was less than the mean for oil. The calculations for the test statistic and the degrees of freedom are given in the slide. Here are the results using Minitab. Notice that the p-value is 0.012. Recall that alpha is 0.01, not 0.05. The next slide includes the conclusions we should draw. When the populations are not independent, we have a situation where the observations are paired. This basically means that the experimental units do not change across the samples. An example of this is any sort of taste test. The variability will be based not only on the difference between the two samples, but also on the preference of the tester. Think about the Pepsi challenge. A person tastes both Pepsi and Coke and then rates the two. Now we would like to run a test to see if there's a difference in the ratings. The problem with doing this with a two-sample independent test is we have no way of removing the person-to-person variability. What if one person really likes soda and another doesn't? The first person may give a much higher rating than the second. This actually is biasing the results. We need some way to adjust for the variability. We will do this by looking at the difference between the scores. This actually turns this from a two-sample problem on the means to a one-sample problem on the differences in means. Let's look at the test statistic. If we assume that the differences are normally distributed, then we can create a test statistic that is in the slide. Now let's look at an example. In this example, each method was used on each blend. This makes it paired because the experimental unit does not change across samples. The experimenter would like to know if the difference between the research blend and the motor blend is equal to 5. Of course, we can't actually test this, but what we will do is set the alternative to be not equal to 5. Here are the solutions. Notice that the p-value is 0.001. You should also notice that the confidence interval does not include 5. What do you think this means? Since the p-value is less than 0.10, we can reject the null hypothesis. From this, we can conclude that there is enough evidence that the difference between the means is different than 5. Now, everything that we have done so far has been based on the sample means. What if we are interested in sample proportions? Next time, we will talk about one-way ANOVA.